Welcome back to AP Daily Videos. Today we'll be looking at topic 7.7, calculating equilibrium concentrations. In this video, we will be looking at how to calculate concentrations or partial pressures of reactants or products using the initial conditions and the equilibrium constant.
Hi, my name is Grant Rushello, and I'm an AP Chemistry student from Bayport High School.
And I'm Lennon Reister, also an AP Chemistry student from Bayport High School.
So before we start, here's some of the key things you're going to want to know. The equilibrium concentration and partial pressures. So the concentrations or partial pressures of molecules within a reaction when it has reached a state of equilibrium, which is when the rate of reactants and products being produced become equal. And this is measured in molars, which M is short for, and that's used in concentration, or ATM for partial pressure. Another thing is the equilibrium constant, which is known as the least constant constant of all constants. This constant is known as K and can be derived from a chemical reaction after the reaction has hit equilibrium by dividing the concentrations or partial pressures of the products by the reactants. And as you can see, there is the equation for it. It's basically products over reactants. And the reaction quotient is expressed as a concentration or partial pressures of products over reactants when the reaction is not yet at equilibrium. If it is at equilibrium, it would be K. As you can see, it's the same equation. You just have to remember that K is when it's at equilibrium and Q is when it's not at equilibrium.
So in this section, you'll notice that there are two types of problems. There'll be one problem where you're given the equilibrium constant and all but one of the equilibrium concentrations or pressures, and you'll need to use the information given to find the other equilibrium concentration or pressure. The second problem you'll see is when you are given all of the initial concentrations and the equilibrium constant, and you need to find the equilibrium concentrations or pressures with the information you're given.
So here's a demo problem to look at to help you envision what we're doing here. Alright, so consider this following reaction. 2-diatomic C is at equilibrium with diatomic A plus 2-diatomic B. And the K for this is 4.00 at 500 degrees Kelvin. At equilibrium, the concentration of diatomic C is 0.30 molar, and the concentration of diatomic B is 0.12 molar. What is the concentration of A2 at equilibrium? So to find this, we're going to use our reaction constant equation, which is the concentration of the products over the concentrations of the reactants. And one important thing to remember is that you want to raise either the products or the reactants to their stoichiometric coefficients. So if you notice that the stoichiometric coefficient to B is 2, then we want to raise the concentration of B to 2 in the equation. So if we plug all the values in, we'll get 4 equals X times 0.12 molar squared, all over 0.30 molar squared. And then if we do some algebra to solve this equation for X, then we would eventually get 31.5789, and then that'll continue, big decimal. And then if we round that to two significant figures, then X would equal 32 molar. And that's how you do that kind of equation.
Alright, so the next type of problem you'll see, as you can see, we're given all of the initial concentrations if you look at the Rice table, but I'm going to bring you back up to the top of the problem, and we're going to look at the reaction that we're given. So diatomic A plus diatomic B is at equilibrium with 2-diatomic C. The equilibrium constant at this point at 2500 degrees Kelvin is at 15. So initially this reaction has partial pressures of diatomic A and diatomic B at 0.350 atmospheres. And C starts with an initial pressure of 0.150 atmospheres. What is the equilibrium pressure of diatomic A, B, and C? So, one of the best ways to attack a problem like this is by setting up a Rice table. As you can see, there's the reaction, initial, change, and equilibrium. So the reaction is simply just detailing like, hey, I have my reactants on the left of the table being diatomic A and diatomic B, and my products on the right hand of the table as seen as diatomic C. The initial is for the initial concentrations, and you can see I have that filled in. I'm noticing that the 0.150, it should have atmospheres right by it as a unit, but anyways, you'll notice that I also have a change row, and you'll notice that I have that filled in already, and you may be wondering how I did that. Well, if we go to the next slide, we need to find the reaction quotient using the equilibrium equation from this reaction, and that equilibrium equation would be the products of the reactants. So we would have diatomic C divided by diatomic A and B. Diatomic A times diatomic B. And as you'll see, the pressure of C is raised to the second power, and that's because of its stoichiometric coefficient. So we now replace Kp with Qp as we are looking for the reaction quotient and not the equilibrium constant, and then we plug in our initial concentrations because Q can be found at anywhere in the reaction. So we simplify and we notice that Q is equal to 0.184. And we notice that Q is less than K. This means the reaction will shift to the right, and if Q was greater than K, the reaction would shift to the left. So if we're thinking back to the situation we're in, by going back to the previous slide, we'll notice that this means that products, there needs to be more products for the equilibrium constant to equal 15. So that means the reactants are going to lose an X amount of pressure, and C is going to gain a 2X amount of pressure. And the reason it's 2X instead of X is because of the stoichiometric coefficient that C has in the equilibrium reaction. From this, we can write out equilibrium expressions to find the equilibrium concentrations of diatomic A, B, and C as seen in the final row of the table. And it's these expressions that can be used to find X. So now for this problem, we again need to reference our equilibrium expression for this overall reaction. Now we want to substitute the values we know. So we know that the equilibrium constant is 15. And we know that the concentration, the equilibrium concentration for diatomic C is 0.150 plus 2x squared because of its stoichiometric coefficient. We then divide that by the reactants, and that being 0.350 minus x, and the reason I have that squared is because the pressures, the partial pressures of diatomic A and B are the same, so essentially it is being squared. Now, since both our numerator and denominator are being squared, we can take the square root of that entire fraction and the square root of the 15. And from there, we want to then multiply each side by 0.350 minus x in order to remove the denominator, or just simply eradicate the fraction, so x will be a lot easier to find. And as we can see, we end up with negative 3.87x plus 1.36 equaling 0.150 plus 2x. We then isolate x and divide by 5.87 to find that x is equal to 0.206. We then can plug x back into the equilibrium expressions for these concentrations, and we can find that the partial pressure of A at equilibrium would be 0.144 atmospheres, and that'd be the same for B. And we find that the partial pressure for C at equilibrium would be 0.562 atmospheres. Now, it's always good to double check that your answer is correct. So you can do this by simply plugging your equilibrium pressures back into the equilibrium expression, and we find that after doing so, that our equilibrium constant is 15.3, which is close enough to 15 to say, yes, there was probably some rounding errors, but we have a good answer.
So some other things to consider. If there is a solid or liquid in the reaction, it is always considered negligible in the equilibrium expression, which means just don't include it. You may have to use a quadratic formula to find the value of x in some problems. And then in these types of problems, the same process is used with both concentration and pressure, only the units are different. And another super important thing that you should know is the x is small approximation. So when the k value is very small, we can make an approximation that x is close enough to 0, so when added or subtracted, it has no impact. You can replace x with 0 in the equation so that it's easier to solve. To find out if this is valid for the equation, what you have to do is take the x value divided by the initial concentration and multiply that by 100. If the resulting percentage that you got is less than 5%, then it is valid to use. This is called the 5% rule.
Alright, so this is our first example of an AP problem. You'll notice that the equilibrium reaction is Bc2 plus 4A2 in equilibrium with Ba4 plus 2A2C, and the equilibrium constant is 1.8 times 10 to the negative 8. That's a pretty small equilibrium constant, so you may want to rewind the video a bit while you're doing this problem to review and really study the excess small approximation description we gave. And you'll notice in this problem there's 0.2 mole of both Bc2 and A2 that are initially injected into a pre-evacuated 2-liter cylinder, and there are no moles of Ba4 or A2C. And the question is asking which chemical species at equilibrium has the greatest concentration. I will now let you stop the video on your own and solve this for yourself. Alright, now that we're back, I'm going to reveal the answer to you. Drumroll, please. The answer is Bc2, will have the greatest concentration at equilibrium. Alright, now I'm going to explain why this is. So, right off the bat, it is always important to make a rice table. And in this case, I have an ice table. And it's always good to figure out which way the reaction is going to move. And I'm sure you're noticing that if I'm going to figure out which way the reaction is moving, then I need to know the initial concentrations. Well, you'll notice that my initial concentrations they look a little different. They're 0.1 instead of 0.2, but that is because we were given the initial concentrations in moles, while initial concentration, when dealing with these equilibrium expressions, needs to be in molars. So to find molars, you divide the moles by the liters of the container you're in to figure out your molars. So 0.2 divided by 2 is equal to 0.1 molars. So it's always good to plug in your initial concentrations into the rice table as seen above. And now we're going to figure out the change. So we need to figure out the equilibrium expression, which you'll notice as Kc equaling products divided by reactants. And since we have no products, the Q is pretty easy to find with Q being 0. And we'll notice that Q is actually less than K, even though our K is incredibly small. 0 is still smaller than something. So, in turn, our reaction shifts to the right, which means the products are going to gain an X amount of concentration, and you'll notice that A2C is gaining 2X, and that is again because of stoichiometric coefficients, and you'll notice that BC2 is losing X, and 4A2 is losing 4X, again because of stoichiometric coefficients. With this information, we can figure out the equilibrium expressions for each concentration, as seen in the equilibrium X row, and now we can use the information we have to find the equilibrium concentrations. So in order to figure out the equilibrium concentrations for each chemical species, we need to again know our equilibrium expression for the reaction, as you can see in the first row. In the second row, you'll notice that I have substituted in everything we know, that being the equilibrium constant, our, known concentrations for our products and our reactants. Though in the third row, you'll notice that I cross out the x, the negative x, and the negative 4x. That is because our equilibrium constant is so small that we can figure that x will be so incredibly small, so when it's added or subtracted, it makes no impact. So that leads to a more simplified version. In the fourth row, you'll notice I just have 0.1 to the fifth. And the reason it's to the fifth is because 0.1 times 0.1 to the fourth is, in a sense, 0.1 to the fifth. So now we want to solve for x by removing fractions. So you multiply by the denominator to eliminate the fraction. And then from there, you'll notice that we need to then solve for x, and 1.8 times 10 to the negative 13th equaling 2x to the third, we need to divide by 2 to get to isolate x, and then we can use the cube root to find x itself, being 5.6 times 10 to the negative fifth. So now that we know our x, we can, in a sense, plug it in for the equilibrium expressions we found for our concentrations, and for BA to BA4, it's just x itself. For A2C, it's 2x, and then for BC2, it's 0.1 minus x, and for A2, 0.1 minus 4x. And you'll notice that I didn't exactly round to significant figures, but that's because it was needed to sort of go beyond what was known in order to figure out the greatest, which chemical species would have the greatest concentration, and that would be BC2, highlighted in blue. Now, to check that our small x approximation was valid, we take 5.6 times 10 to the negative fifth, divided by 0.1, as 0.1 was our initial concentration, multiply that by 100 for a percentage, and we get 0.056, which is well below 5%, so the x's small approximation is valid.
All right, so here's another AP problem to consider, and this one's going to be an FRQ. So consider this following reaction. PCl3 plus Cl2 is at equilibrium with PCl, and the K value, or the equilibrium constant, is 0.24. So a 0.50 mole sample of PCl3 and a 0.60 mole sample of Cl2 are placed in a previously evacuated 1 liter rigid container, and the reaction represented above takes place. At equilibrium, the concentration of PCl5 in the container is 0.030 molar. So for A, on the graph to the left, you're going to need to draw 3 curves that represent the changes in concentration of each gas as the reaction reaches equilibrium. And for B, explain how the slopes of these curves at equilibrium can represent how the forward and reverse rates of the reaction become the same at equilibrium. Alright, so I'm going to pause it for a little bit, and you guys can try this on your own. And we'll be right back. Alright, so now that we're back, let's look at the answers. So, the first thing we're going to need to do is plug all our information into the rice table. So, we know the initial concentrations of our reactants, and we can assume that there is 0 of the products because we are given no information for it. And as there is 0 of the products, we can assume that the reaction is going to progress to the right, meaning that the reactants are going to have a negative X change and the products are going to have a positive X change. And so we already know what the equilibrium value for the PCl5 is. It's 0.03 molars. However, we don't know the equilibrium values for the reactants. All we know is that it's 0.50 minus X and 0.60 minus X. So what we're going to do is plug this into our reaction constant equation. So that would be 0.24 equals 0.030 all over 0.50 minus x times 0.60 minus x. And then we're going to combine those the terms on the denominator. And then what we're going to do is multiply both sides by the denominator of the fraction on the right side. So we'll get 0.24x minus 0.264x plus 0.042 equals 0. As you might see, we are unfortunately going to have to do the quadratic formula for this one. So I hope you know what the quadratic formula is. If you don't, it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And then the a value would be what's in front of the x squared. The b value is what's in front of the x, and the c is that last number. So once we plug all those values into the quadratic equation, we get that on what you see on the third line down in the middle row. And then so we're going to do some algebra to solve this, and once you finish solving it, it's going to be x equals 0.64 plus or minus 0.029 all over 0.48. And so we solve this, and then we get x equals 0.61 or 0.49. However, we know it has to be 0.49 because if it was 0.61, then we would end up with negative concentrations at equilibrium, which is physically impossible. So we know it has to be 0.49. And then we plug it into the x, and we can find the equilibrium values or concentrations for the reactants. And that would be 0.010 molars for PCl3 and 0.11 molars for Cl2. And so when we put all this information on a graph, I first plugged in the initial values on the far left-hand side of the graph, and I put in the values at equilibrium on the line that says equilibrium, obviously. And that's what the graph is going to look like. And then so the answer to B, your answer might be a little bit different than this, but it should have the same idea. I said the slope of all the curves becomes 0 at equilibrium. This means the concentration of both the reactants and the products are constant and mostly consistent at equilibrium. In turn, this shows that the rate of the forward and reverse reactions are also the same at this point. And so for the summary, K is equal to the products over reactants concentrations or pressures at equilibrium. You should always use a rice table to help organize information and help yourself with solving problems. Remember to raise concentrations and pressures to the power of their stoichiometric coefficients. That's very important. The same process is used for both pressure and concentration. You may have to use a quadratic formula when solving for x. That may pop up every now and then. And the x is small approximation can be applied when x is small. You're going to see that every now and then, something you should know. And that's it.
Thanks for watching our AP Daily video. We'll see you next time.